Okay, everyone. So we've got, today is just a review day for the exam. You can take the exam on Dropbox anytime this week until Friday. There's 20 questions, I believe, and you have 75 minutes to take it, one attempt. Since we're doing the exam online, I'm not going to present any new material today. I'm just going to do a review. I was going to start out by talking about quiz 3 and then just go through the lecture slides for the material covered by the exam. And if you have any questions, feel free to ask. How is lab 2 going? Is any problems with lab 2? Everyone have it done? Sorry?
I said I figured it out finally, Saturday morning.
Oh, good, okay. Anyone stuck on lab 2? Okay, so lab 2 is due today, so we want you to submit your helloworld.c on Dropbox by tonight, and then we'll spend this week in lab demoing, doing demos for lab 2. Okay, and I wanted to start out, and I had a few questions. It looks like everyone in here might already be done. But there was a few questions I got about the dim period versus the PWM period and what the difference was. So I made this little graphic to try to show that. So just to quickly go through this, in this case I'm trying to show what's going on with the LED lights. The problem is that there are two time scales involved. The first is the PWM period, which is like 10 kilohertz. So the 10 kilohertz being the frequency, the period is the inverse of that. So 1 over 10 kilohertz, I think, is 10 microseconds. And so that's the PWM period. And the PWM period is the frequency at which the LEDs are blinking, right? But they're blinking really fast, like they're blinking every 10 microseconds. And then the duty cycle should determine how dim the LEDs appear when you look at them. Okay, so the duty cycle is how long the signal is high versus low within the PWM period. And then you've got the dim period, which is the time it takes for the dimness to go from full on 100% brightness down to 0 and then back up to 100%, right? So, and that is going to happen like over the course of, say, 2 seconds or a second, right? So that's a much longer time scale. So it's hard to depict something like that graphically, but I tried to do that here. So the idea is that you've got the PWM period, and generally speaking, the PWM period is going to have the same duty cycle for a long time, a lot of periods before it changes, but it will eventually change. And so, for example, in this case, I'm showing it's 70% on, 70% on, and then in this third period, it switches to 69% on, and then it's 31% off, and then it continues to go down from there until eventually it reaches 1% on, 99% off, 0% on, 100% off, 0% on, 100% off, right? So in this case, each value of the duty cycle is repeating twice for every percentage you change it. Now in practice, it's going to probably repeat more than twice. You guys with me? Okay. So the idea is that the dim period is going to be actually that's wrong now, sorry. The dimming period is the period it takes to go through a full cycle of duty cycles, a full range of duty cycles. So in this case, I said the dim period is 200 times that of the PWM frequency, but actually it's not 200 times that, it's 400 times that, because each one of these duty cycles is repeating twice. You guys with me? So that should have been, when I originally did this, I was going to make it 200, but it's actually 400. Okay, so the way it's set up now, the dim period is, the time scale of the dim period is 400 times. It's 400 times slower than the PWM period, right? Which is 1 over the PWM frequency. Does it make sense? And that's just the way that it's set up at the moment. Now you can increase the PWM frequency, or you can increase the dim period, which would, change this relationship, right? But the point is that the dim period is, it's generally going to be at least 200 times that of the PWM frequency and possibly more. So the trick here is, the trick for your code is to figure out how often to change the duty cycle as you're processing the PWM signal. So the one way to do that is to take the dim period and divide it by 200, because there's 100 percentages, you go down and then 100 back up again. So there's 200 sort of increments. And if you divide that by the PWM period, that just gives you a ratio between how often you change the duty cycle to how many of these pulses you put out. Does that make sense? Okay, so just keep that in mind, because you can structure your loop in your code to just keep track of this number, this ratio. This is the important ratio. And then every time you have iterated over the PWM period that many times, you adjust your duty cycle. Okay? Does that make sense? Hopefully, if you're still working on that, hopefully that's a hint. Okay, so quiz 3 was due, I think, last week, but I told you that we would wait till today to go over it. So the first question on there, what is the result of one device driving a wire to logic 0 and another device driving the same wire to logic 1 using a push-pull driver? So the idea is that you have one wire and it's in conflict because you have two drivers driving the same wire, and there's a disagreement. One's trying to set it to 1, one's trying to set it to 0. And if you have a push-pull driver, what that's doing is it's creating a low impedance path on that wire both to VDD and to ground, which creates a low impedance path between VDD and ground, but the path is going through one of the drivers on the pull-up leg and then through the pull-down leg on the other driver that's trying to set that wire to 0. So this is, you might think, why is this important? Why are you emphasizing this so much? This is the reason why we use open drain drivers for I²C. But in the case, in system Verilog, it's also important because in system Verilog, it's assumed by the language that all drivers are push-pull drivers. So when you write code in HDL, VHDL or Verilog, you have to avoid this double driving or contention or conflict problem because, like I said, it's a single-ended push-pull style drivers in general with system Verilog. You might say, wait a minute, does that mean that you can't do open drain in Verilog? You can, but to do that you have to take advantage of the Z value in Verilog, which I haven't talked about that yet, but there's a special way to handle that in Verilog where you can set a wire to be high impedance Z. But if you're just setting wires to 0 or 1 and you set 1 to 0 and 1 to 1, you end up with the same problem you do with SPI, for instance, when you have contention. Yes?
So in order for this one to work, they both have to be 0 or they both have to be 1?
Yeah, that would work, but even then you don't want to, it's not good to even do that. I mean, generally speaking, you should have one driver per signal. Okay. So every signal should only be set by one thing, but it can be read by multiple things, right? Okay. Oh, by the way, so just to be clear, in system Verilog, this would be like an always statement, for instance, and this could be like an assign statement, for instance, and each one of those representing a circuit that's driving an output. Okay, so what is the answer? The answer is undefined. Undefined, because in an analog sense, assuming that the impedance of this pull-up transistor and the pull-down transistor are about equal, then the voltage level would be somewhere in the middle between, the 0 and the 1 value. So if it's like a 5-volt system, it would be, say, 2.5 volts, for instance. So that would be an undefined value. Okay, what does a 1-bit signify in the RW slot of an I2C transaction? So a 1-bit is the bit that is normally at the end, right? So that is, so the address is going to be 1, 2, 3, 4, 5, 6, 7. The first 7 bits is the address in the header. And then you have the read-write bit, and then the acknowledge. So the read-write bit is the 8th bit that's transmitted on an I2C transaction, and a 1 would mean read. Read is 1, write is 0. Now with SPI, it can be whatever you want it to be, as long as obviously both ends should agree on that, right? Both endpoints. With I2C, that is defined as part of the protocol. You guys with me? So what is read and what is write and which bit do we use to designate that? With SPI, it's vague, right? Because it's up to the application. Whereas with I2C, it's baked in to the protocol. So read is 1, write is 0, and honestly, I never remember that. I always have to look it up. But the exam is, open notes, so make sure you have that handy. In an I2C channel, what is the value of the SCL wire when there are no transactions in progress? The SCL is the clock, but it wouldn't have mattered if I said SCL or SDA, because if there's no transactions, the open drain drivers are not pulling down. The only option they have is to pull down, which means that the voltage is going to be resulting from a voltage divider between a 10 ohm on the high side and hundreds of thousands of ohms or mega ohms on the low side, right? So if you look at this like a voltage divider, that output wire is going to look like a 1, a logic 1. It's going to be near the power supply voltage. There's going to be a drop, but it's only the drop over this 10 kilo ohm resistor. So there will be a slight voltage drop there, but it should be safely outside of what's called the forbidden zone, which is the voltage values right in the middle between 0 and 1. Okay, so the answer is logic 1. What is the result of 2 devices driving a single wire to logic 1 using a push-pull? Well, this is a little bit of a misleading question because you don't actually drive. Oh, sorry, never mind. No, this is push-pull. Never mind. Push-pull. So with push-pull, you do pull up, right? So 2 devices trying to drive a signal wire to logic 1, meaning they're both pulling up, so it'll be 1, right? They're both driving one wire. That's not good, but at least they're both driving to 1, so the logic level will be 1. But you want to avoid that situation. What is the result of one device driving a wire to logic 0, another device driving the same wire to logic 1 using an open drain driver? Okay, this is the one that's a little bit strangely worded because you can't actually drive a signal up to 1 with open drain. You basically just leave it alone and it naturally goes to 1. But if one side is doing that and the other side is pulling down to 0, then it's not a problem. It's just the logic value is 0. Make sense? So in other words, what I'm trying to say is that if there is a contention on an open drain circuit, the value is going to be determinate, will be a 0, right? So contention on open drain means 0, right? Contention on push-pull means smoke, basically. Okay, it means your chip is fried. But contention on open drain, no problem. It just gets interpreted as a 0, low voltage, logic low, logic 0. Okay, what's the start signal? So I2C, this is in my opinion, this is the most confusing part of I2C. What is the start signal? It's when you drive the data signal low. Now remember, the data signal is normally high when it's idle. So it's idle, so we drive it low while the clock is still high. That indicates that that you're trying to take mastership of the bus. Remember, normally during the transaction, the data does not change when the clock is high. Right? The data is supposed to be frozen whenever the clock is high. So changing the data when the clock is high means start or stop. Start or stop signal, right? Stop Stop signal, drive SDA high while the clock is high. So if you drive it low while the clock is high, it's the start. You drive it high while the clock is high, it's stop, right? So data. When the data is driven low when the clock is high, that's start. When you drive the data high when the clock is high, that's stop. How many times does control of the data SDA change during a single byte I2C read operation? Now this is different depending on if you're reading or writing. So if you're reading, it's 2 times, because the first time you change control is when the master yields control for the acknowledge after the header byte. And then the slave side has to yield control when the master acknowledges, right? Yeah. So header acknowledgement switches from master to slave. Data acknowledgement switches from slave to master. I think if it was a read operation, if I had asked you how many times does it change control during a read, that would be changes control. The header acknowledge, this is the same. So you get a yield of control after the header, right? But then you have to yield control right after that so the master can then send their output data. And then the slave has to acknowledge it. So the answer would be 3 times if I said write operation. So if it's an I2C write, you change control 3 times. I2C read, it's 2 times. Which, okay, there we go. Yeah, that's the right, 3 times. Okay, what's happening during the following I2C transaction? These ones are a little bit easier to read, I think, because all you have to do is look for when the clock is high and write down the corresponding value on SDA. Well, that'll at least give you the bits, right? You don't really know what's going on, but at least you have the bits. To figure out what's going on here, you have to count 8 bits in. 1, 2, 3, 4, 5, 6, 7, 8. So that's your read or write bit, and it's a 0, which means we're writing, right? So we're writing, and the address we're writing to is it's a 7-bit, so it would be 4F. Right? 4 is 100, F is 1111. So 4F is the address that we're writing, and the data we're writing is that's the acknowledgement. So we start here. So 0011 is a 3, 1011 is an A, so 3A. Make sense? So we're writing 3A to address 4F. Now, are we getting acknowledgements? Well, remember, the acknowledgement is 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have a 0 acknowledge. And we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 0 acknowledge. So we have a 0 acknowledge after the first byte and the second byte, right? Yeah. So there we go. How can a collision between 2 I2C hosts be detected? You can drive the data low to try to create a start signal and claim mastership, right? And then you can check to see if someone else drove the clock low. Because normally if you were going to take mastership, you drive the SDA low, and then you would then drive the SCL, the clock low after that, right? Make sense? Now the problem with this, by the way, is that what happens if everyone uses this same policy? Like if everyone's doing this, then you know, would that work? I mean, you drive SDA low, you wait for someone else to drive SCL low. I guess it would work as long as they don't exactly wait the same. They don't wait exactly the same amount of time, because if they did, well, assuming they didn't start at exactly the same amount of time, and wait the same amount of time, right? Because then they would be perfectly synchronized. But the chance of that happening is very small, right? Because they would have to start the transaction at exactly the same time, and they'd have to wait at exactly the same time. And it's very unlikely that two hosts are going to start at exactly the same time, right? They're usually going to be, because they're different chips, right? Okay, on an I2C read transaction, which side drives the clock? The master. In fact, the master always drives the clock. You might notice, if you ever look up anything about I2C, you might read about, there's a thing called clock, what's it called? Clock stretching. And that's when the slave side grabs hold of the clock to delay the master, to stall the master. There is that's something that can be done, but for the purpose of this class, we'll just say the master drives the clock. What's the limitation for adding additional devices to a single I2C channel? There's a leakage current issue. Open drain, you're going to have leakage current. There's also a limited number of I2C addresses. There's only 7 bits in the address, right? Now there is an extended mode. There is a 10-bit mode for the address on I2C. I didn't cover it, but even then, still that's not many addresses, right? Not many unique addresses. Now there's ways to work around that, though. By the way, but in general, there's a limited address space, and then the collision rate will increase because if you had a bunch of hosts on that I2C and they're all they're all sharing the same 2 wires, there's an increased chance of collisions or contention on the bus. Master sees a 1-bit during the acknowledgement slot of the data phase. What does it mean? It means the write address was received, but the data was not. So the data phase, there's separate acknowledgements for the address phase and the data phase. And the 1 bit means not acknowledge, right? In this case, we had 0 acknowledges, right? 0-bit acknowledge, which means acknowledge, right? 1 means not acknowledge. What you might say, well, why make it active low? Well, because the idea there is that if no one's listening, remember that the natural state of this is 1, right? With the open drain. So if no one's listening, then it's going to be a 1. So it's kind of the acknowledgement. If no one's listening, the acknowledgement bit will be 1. Will be read as 1. Okay. Master sees a 1-bit. Okay, we got that. How many bit slots comprise a single byte I2C transaction, not including the start and stop signals? Well, it's 9 bits and 9 bits, right? 18. Okay, that's it. Any questions? Okay, so I'm just going to run through the slides just to review some stuff from the beginning of the semester. The exam doesn't cover system Verilog, it just covers the interfacing phase of the course. So make sure you remember how programmed I/O works. So we didn't really talk about the mechanics of how this works. All I said is that in programmed I/O, you assume that there is some kind of read-write interface where you can read an address or write an address, right? I didn't talk about what obviously SPI provides a way to do that, and I2C provides a way to do that. But generally speaking, with a system on chip like this, like I'm showing here, these buses are parallel buses. They're not serial buses. Serial buses are usually used for off-chip access. You guys with me? Like you wouldn't use a serial interface for on-chip communication because they're too slow. Right? Parallel buses are faster because you're sending multiple bits in each cycle, right? But I haven't talked too much about parallel buses, but the point of this is that each peripheral has a special range, and then we can read or write to that range in order to perform communication between the CPU and the peripheral. Make sense? So this is still kind of a master-slave style interface. Seems kind of weird, though, that it's based on addresses. But the reason they do that is because the CPU is accessing this bus through load or store instructions. So this is the reason why when you guys took 212 and you learned about computer architecture, you talked about load and store instructions and arithmetic instructions and control instructions, but you never talked about I/O. Like, how do you do I/O? How's the thing, CPU can interact with memory, but how does it interact with the outside world? Well, that's because it does it through load and store instructions. It just does it through these special address ranges. And of course interrupts as well, but we also talked about interrupts. The next section is bit twiddling, where we talked about how to manipulate single bits or ranges of bits within a word using C. But of course C, as you guys know, using C is very similar to using assembly language. It's such a low-level language. So we talked a lot about that because when you use programmed I/O, each of the bits in the values you're doing programmed I/O with often will represent specific flags, right? Like you read a flag from the keyboard peripheral and it'll tell you whether someone hit a key, that sort of thing. So you have to be able to extract bits. And so this is when you use shift instructions and bit masking, bitwise logical operations. So in this case, we are setting a bit. We're setting bit 2 in this thing val, leaving the other bits alone. In this case, we're clearing a bit, clearing bit 2, using a bitwise AND and a logical bitwise negation. Here we're isolating a specific bit by shifting it down to the right-hand side of the register or variable, and then doing a bitwise AND to filter out everything but that last bit. Here we were isolating bit 3, not by shifting, but by just doing a simple bit mask operation, because in this case we only cared about the logical value, true or false, not, just wanted to use this to, like, in an if statement. Everyone with me? Okay. This is bit fields can be isolated by shifting to the right according to the right or the least significant bit. So this is bits 5 down to 3. So we shift 3 bits to the right. Why 3? Because it's 5 down to 3. So 3 is the least significant bit of the bit field, and we want to put that in the least significant bit of the output. So we shift by 3 bits to the right, which will adjust bit 3 to become bit 0, and it'll adjust bit 5 to become bit 2. So after we do this shift, bits 5 down to 3 will become bits 2 down to 0 after the shift. And then all that's left to do is filter out all but the low order 3 bits, which you have to do with another bit masking operation, right? So you have to AND it with 1, 1, 1, right? Now how do you get 1, 1, 1? Well, you can just type 7, right? But the problem with that is that what happens if we don't know when we're writing the program how many bits there are? Right? If we don't know ahead of time how many bits there are, we need a way to get 7 from 3. So the way you do that is you take 1, shift to the left by 3, and subtract 1. Or shift to the left by however many 1 bits you want. So if I want, say, 7 1 bits, I would take 1, shift to the left by 7, which would become 128. Then I would subtract 1, that would give me 127, and 127 is 7 1 bits. Okay? Okay, so that summarizes that. Loading and storing in C is a load is a dereference operation with star, and a store is also a dereference operation with star, except you use it on the left-hand side of an assignment. So this is load, and that's store. These get translated to load and store. You guys know, though, from the Cordis tools that we're using that you don't necessarily want to do programmed I/O this way, depending on the architecture. Sometimes there's special instructions. So I don't know if I think I showed in class when I was doing the demo, but in the Neos 2 instruction set, there's a load word and store word, and there's also load word I/O and store word I/O, right? So in order to get this would give you a load word or store word, but if you want to do load word I/O, you have to use the intrinsic, which is, what was it? I don't remember. Read something? Read, there was special macros for that. Read 32, write 32, right? Whatever the macros were that I showed you in class. My memory is shot these days. I have to look that stuff up. But there were special, what are called intrinsics to use. Now you might say, who cares which one you use? What's the difference? The difference is whether or not you want to be careful that that these operations don't get intercepted by the cache. You don't want programmed I/O to be subject to cache, right? So often, there's a special variant that bypasses cache. Now you might say, well, wait a second, then you lied. You said that it was load or store is how you interact with hardware. Yeah, but it is load or store. It's still accessing things through reading and writing of addresses. But when you do programmed I/O, some architectures have a special variant of the load or store specifically for I/O, right? And you might say, as opposed to what? Well, as opposed to memory. Like you load and store to memory or load and store to a hardware device, right? That's the difference, right? Okay. Here it is. I/O write 32. That's what I was looking for. Yeah. I/O read 32 and I/O write 32. Okay. So there was an example of that. Skip over this. Okay. Pulse width modulation is, obviously the topic of Lab 2. You might be wondering, why are we focusing on this so much? This seems to be pretty trivial. Actually, in cyber physical systems, which would include any kind of power electronics, which include essentially, well, almost any voltage regulator power supply ever, anywhere, uses this. Any kind of DC to DC converter, AC to DC converter, AC to AC converter, a lot of converters circuits use pulse width modulation, as well as motors, actuators. Anytime you have a computer that controls something mechanical, it's almost always based on pulse width modulation. Not only that, but you can use pulse width modulation for audio. In fact, if you have what's called a Class D amplifier, which some cars have, or home audio systems, Class D amplifiers, those ones are basically they use pulse width modulation to create the analog signal that is played on your speakers. This literally is how you get audio. Now, if you use this for audio applications, you do have to put a low-pass filter on the outside of that to eliminate artifacts from these sharp edges. But yeah, pulse width modulation is very, very, very common. So it's important that that you understand this. Hopefully, in Lab 4, we'll use this to control a motor. That's my plan. Oh, by the way, if you ever get one of those greeting cards at the drugstore that play music, like you open up the card and it plays a song, those ones just use direct pulse width modulation. They don't have that little filter. That's why they sound a little tinny and weird, but they sound okay. But they literally just have an 8-bit processor, same one that they have in Arduinos. It's the Atmel processor. So when you go to the drugstore and you buy a greeting card that plays music, that's an Arduino processor using pulse width modulation directly connected to a speaker to play that song. That's how it works. But anyway, oh yeah, what is it? By the way, yeah, we know there's a period and then there's an uptime and a downtime, and the uptime is a percentage of the period, and that's your analog value as represented as a ratio between 0 and whatever the 1 voltage is. So obviously PWM is limited to having a upper limit of whatever the maximum, whatever the 1 voltage is, right? So, you can't use this for, you can't output a big voltage, but if you use this to control something like an H bridge or a power electronic circuit, then you can, end up achieving high voltages with this. Okay. What analog voltage is generated through? Okay, it's 30% duty cycle. You just multiply 30% times 3.3. Okay, interrupts is a signal from a peripheral. It's a way for a peripheral to get the attention of a processor. This is the same way interrupts have been around for 50 years. This is the way that you get the CPU's attention. Like when you pull your phone out and touch the screen, it's an interrupt. And so interrupt is a signal, and it causes the CPU to jump unconditionally into an interrupt handler, which then does a little bit of forensics to figure out what caused the interrupt, and then it services the interrupt, does something in response to it. The problem is that the interrupt generator and the CPU are asynchronous. You know, they're two separate hardware devices. So you run into some issues when, for example, you know, if the interrupt sender gets a little too aggressive with the interrupts, you know, you might end up live locking the CPU. You might interrupt it so often that it can't do anything else, right? That's the way a denial of service attack works. If I want to bring down Amazon, I get a bot network in the internet, and I just have them send packets so fast to Amazon. Every time a packet arrives, it triggers an interrupt on their server, and interrupts are serviced by the operating system, which have the highest priority. So when you're servicing an interrupt, nothing else can happen, and I can, you know, take down a website that way. It's just cause them to constantly be servicing interrupts. So we talked about different ways the interrupts can be set up. So there's level triggered that respond to the level of the interrupt signal, edge triggered, which respond to the edge of the interrupt signal, and we also talked about acknowledgement mechanisms where you can have a signal from the CPU back to the interrupt sender that tells it, okay, I see your interrupt, chill, I'm getting to it. And so the idea is that you raise the interrupt, the CPU, after it goes into the interrupt service routine, it can raise the acknowledgement, which tells the sender that the CPU is on it and that it can lower its interrupt, right? And then it also indicates to the interrupt sender how long it takes the CPU to service that interrupt, because usually towards the end of the interrupt service routine, it'll drop the acknowledgement, right? So you get like a little handshake there. The Atmel chips do not do that. They don't have that acknowledge. I believe the Neos does, though. So it depends on the processor. Okay. Okay, so then for bus protocols, we had asynchronous and synchronous. That was basically just whether or not you have a clock in the channel. So why don't we always have a clock? We should always have a clock. Why not always have a clock? The clock complicates things. It's a high frequency signal, right? There may be a lot of capacitance, which makes it hard to run the clock. It takes another wire, right? So, some protocols are asynchronous. So we talked about UART, which was asynchronous, and so the way it was able to get around having a clock was that both ends just had to agree on a baud rate, right? Which is a constant issue with UART. If any of you have ever used UART, you almost never know what that's supposed to be, and it ends up being a trial and error thing. You know, you plug into your power distribution unit in your rack, which has a console input that's UART. You plug it in, and it's like, all right, well, let's try 9600. Nothing. All right, let's try. You try different values there till you get it. And then for synchronous, SPI, I2C, and JTAG all had clocks in the channel. So SPI was 4 signals: S clock, MOSI, MISO, and SS. MOSI and MISO were just the full duplex bidirectional signals between the master and slave. If you have multiple slaves, MISO becomes a bit of an issue. How you're going to handle that? There's also a slave select that is used to explicitly start the transaction up. And then, of course, the clock. The master drives the clock. And then, of course, SPI is bit serial. It acts like a shift register. And then finally, this was the kind of the most confusing part of SPI was the fact that there are 4 different modes depending on C-pull and C-fa. C-pull is the default state of the clock. So C-pull of 0 means the clock is usually, is low. C-pull of 1 is the clock is usually high if there's no transactions. And that also will tell you what the first edge of the clock is. And then C-fa is whether you read on the first or second edge of the clock, or start reading on the first or second edge of the clock. Make sense? You guys with me? Everyone remember that? Okay. So of course, we covered that in Lab 1. And then SPI is doesn't really have a notion of a read-or-write transaction, so we had to kind of hack that on top of it. So there's this notion of an SPI exchange, which is just the exchanging of bits between the two ends. And then transaction is when you build a read-or-write protocol on top of that, which is a little, awkward, a little strange, a little inefficient, because whenever you do a transaction, one of the pins, MOSI or MISO, is unused. So you're basically creating a transaction protocol that's half duplex on top of a full duplex technology, meaning that you never use the full capabilities of SPI. Kind of hacky, but that's how it's done. Strange, but yeah, if I do a read, then during the data phase, the master doesn't send any data, and during a write operation during the data phase, the slave doesn't send any data. So, you're kind of not using the full capabilities, but that's the only way to do reads or writes. Okay, and then so there's some. You can expect to see a question about this on the exam. So if I give you a timing, and the other nice thing about these types of questions is you kind of get practice reading timing diagrams, which is something you do constantly when you start writing code in Verilog and doing hardware designs. So you've got a timing diagram here, and you start from left, work your way to the right. You can see, the first thing that happens is the slave select drops, and then the clock drops there's a falling edge from high to low. And in this case, obviously C-pull is 1 because the clock was high before the transaction began, and C-fa is 1, and you can actually tell that from the timing diagram, because if C-fa were 0, you would have seen SS and clock change at the same time. So I didn't actually even have to put this information, the C-pull and C-fa in here. You can tell from here, from looking at the timing diagram. Now, the most significant bit first or least significant bit first is something you would have to know to answer this question. So that would just depend on what order the bits are, or each of the bits in each byte are sent. Most significant bit first means that you would just read it, from left to right. Whereas if I put least significant bit first, it would be the opposite order. Also, you can kind of tell that this is a write operation just from the waveform, because you can see there's no data. The slave side doesn't ever send any data. Now, it could also be a read and the value that was read was 0. So, that can be a little misleading. But on the other hand, you can also see there's activity here on the master side during the second byte. So, yeah, it's definitely a write. Okay, and then the multiple reads is where you have a streaming bit, and you can do multiple reads or writes. We had covered that in the lab. And then you can have multiple slaves with SPI, but you have to decide whether you want to do separate slave selects or one slave select with a daisy chain, where you basically treat all of these guys as one, right? Okay, and then let's see, we talked about lab 1, and then we talked about UART. We have a start bit, and always one start bit? Yes, always one start bit. sometimes more than one stop bit. Start bit is a 0, because the channel, just like I squared Z, the channel defaults to 1. But it's a push-pull interface, so it's 1 because someone's driving it to 1. You guys with me? It's not 1 because there's a pull-up. It has to be actively driven to 1 because there's a pull-up transistor here. Yeah. So, and then there's a parity bit, which is optional, and both sides have to agree on the clock speed. So there's no clock. There is typically a ground line, though, that has to be shared between the two sides, which would be also true in SPI and I squared C. I just never, for some reason, the only time I showed the ground was, oh, maybe I don't show it. Oh, never mind. I guess I don't show it. Yeah. So, but there's 2 wires that carry data, transmit and receive, and you only actually need to have one of them if you only want to send data one direction. Okay, so the most confusing part, in my opinion, with UART is this parity bit. So the parity bit can be, you can have either even or odd parity, but the parity does not indicate whether there was, is not set to 1 if you have, for example, odd parity and you have an odd number of 1 bits in the data. It's actually set to 1 if there's an even number of bits in the data, because the objective with the parity bit is to have the number of 1 bits inside of the data and the parity together be even or odd. Make sense? So you could think of the parity bit actually as just kind of the active low, essentially. Like if you have odd parity, then if there's an odd number of 1 bits in the data, then the parity bit will be low, meaning, so you could think of it that way if you want, or you can just think of it like I do, which is it's the data plus parity. Does that make sense? Hopefully I didn't confuse everyone with that. But that's the and the parity is optional with UART, as well as even the number of bits in the transaction. Although typically it's 8 bits. If you calculate the throughput as a function of baud rate is the channel speed, but inclusive of the start and stop and parity. So those don't convey data. So if you want to calculate the throughput, you have to take the number of data bits divided by the total bits and multiply it by the baud rate. So for example, 9600 baud, if you have 7 data bits, 1 parity bit, 1 stop bit, that would be actually 10 total bits, because you have to include the start bit in here as well. I didn't list that because I was trying to trick you in the question. So start, stop, parity, that's 3. 3 plus 7 is 10. So 7/10 times 9600 baud would be 6,720 bits per second. And that's, of course, assuming that you have, that's assuming that you're fully utilizing the channel, that you have 1 byte, one transaction after another, right, with no space in between. Okay. Any questions about UART? Okay, and then SPI, multi-SPI. Oh, sorry, this was the motivation for the open drain. Right, so transistors, you have NMOS and PMOS. They act like electronic switches. They're controlled by a gate, and they short the drain and source whenever the gate tells them to be shorted, right? But the gate signal that does that is different on NMOS versus PMOS. NMOS, a gate of 1 connects, turns on the switch, and in PMOS, a gate of 0 connects, right? Which is why there's a little bubble there. It's a little 211 style knot bubble. CMOS, which stands for complementary MOS, metal oxide semiconductor, is whenever you have a circuit that has an output that is controlled by a pull-up network and a pull-down network, where the pull-up network is comprised entirely of NMOS, and the pull-down network is comprised entirely of, pull-up is PMOS, pull-down is NMOS, right? And so I only mention this because with a push-pull driver is actually a CMOS inverter, So you have an input here that's connected to both gates, and if that input is 0, it's going to turn on the PMOS and pull up, right? And an input of 1 pulls down, right? Right. Or you can have, if you don't want to invert, you can just have 2 of these in series, in which case you don't have that inversion between the input and the output. But the point is either way, you're actively pulling up the output to 1 or 0, and so you have to be careful that you don't have, you know, a pull up and a pull down on the same wire. And so that's why we have the open drain interface, and I2C uses that. That basically allows the bus to be multi-master. And so I2C, as we talked about with quiz 3, has a start signal, 7 address bits, read or write bit. There's an acknowledgement after that, and then there's the data, and then another acknowledgement. Master always drives the clock. The master and slave kind of trade off on the data. And the read-write, as I mentioned, is 1 is read, 0 is write. Acknowledgement is a 0 means acknowledge. 0 means acknowledge. And the way to remember that is that if you don't have anyone listening, the default state of the bus, the data is going to be 1. So if no one's listening, you're going to have a 1 there during the acknowledgement slot, and that would, you know, you don't want there to be an acknowledgement if no one's listening, if no one's actually responding. Okay, and then JTAG is designed for testing and debugging. We use JTAG in class in the lab. It's what powers your FPGA programming. That's how you program the FPGA. That's also how you debug programs on the FPGA. It's how the console works because, and this is the cool thing, you probably noticed this, that in Platform Designer there's a thing called UART over JTAG or something, JTAG UART something, I forget what it's called. But the idea is that it's UART, which is one protocol that we looked at, but it's somehow it's running over top of JTAG. Like JTAG, the JTAG protocol is conveying the UART protocol. How does that work? I have no idea. I always wondered how that worked. But the reason it does that is because the device on the FPGA board that we're talking to is called a USB blaster. The USB blaster is actually putting JTAG over top of USB. So the way it really works is you have USB on the bottom level, you have JTAG on top of that, right? And then you have UART on top of the JTAG, right? Kind of complicated. It also explains why things are kind of clunky when you're communicating with the board, right? Now you might say, well, why not just go straight JTAG? Because modern PCs don't have a JTAG output on them. That's why. Right? If they did, there would be a 4-wire ribbon connector coming off of the PC on the board. But basically, every I/O device these days uses USB. So it does JTAG on top of USB. So that's what we're dealing with. But JTAG has 4 wires minimally. There's some optional wires. But the thing that's neat about JTAG is that you create a chain with it. So it's very similar to using SPI in daisy chain mode. The difference, though, is that instead of having that slave select, they have this thing called test mode select, TMS. And TMS is not just a binary 0 or 1. Well, it is because it's a 1-bit signal. But it's read over across multiple clock cycles. So you put a sequence out on TMS to put the devices in the JTAG chain in a certain mode, a certain state. And this is the state diagram. Now that looks kind of complicated, but, and I'm not sure, you guys probably haven't done a lot of state machine design. You should have in 211, but they kind of dropped that at some point over the years. But the idea is that each one of these bubbles is a state. It's the mode that each device in the JTAG chain can be in at any time, right? And to change it to do a different mode, you just put a sequence of bits in with TMS, right? So if I start out here, if they're in this kind of reset state, and I want to go to the pause data register state, I have to get there, right? I have to jump there. And so each one of these states has 2 outgoing transitions because there's only 1 bit, right? TMS is 1 bit. So from each one of these states, I can go to 2 other states. That's it, just 2, based on the TMS. So if I'm in this state and I leave TMS 1, I'll just stay there. But if TMS is 0 and I clock it, I'll go here. Now if I switch TMS to 0, keep it at 0, I'll stay here, run idle, run test idle. Or if I set TMS to 1, I'll go to here, right? And then if I set TMS to 0, I'll go here. If I leave it at 0, I'll go here, right? So I can move all of the devices in the JTAG chain to different modes depending on the sequence of TMS values across multiple clock cycles. And this is a synchronous protocol, so I provide the clock too. That's the nice thing. So I can even determine how fast I change states because it depends on how fast I drive the clock, right? Now once I'm in a state, then it's very simple. You've just got a big shift register. You've got data in, data out. So bits are just shifted through the whole chain. So the more devices on the train, the more cycles I have to shift bits in, right? So also the more bits, so for the way this relates to you guys is that the FPGA is configured by shifting these bits in, right? Now the FPGA, think about this, it has 115,000 logic gates, right? Each logic gate is a 7-input lookup table to make a single 7-input logic gate. So each LUT is 7 bits and there's 115,000. So just to program the logic gates on the FPGA, I'm going to have to send 115,000 times 7. But there's other configuration bits on the FPGA as well, like all the memories, MUX settings, routing fabric setup, right? There's millions and millions of bits that I have to configure, which is why when you program the FPGA, it takes a while. You have to sit there. It takes like, what, 10 seconds? Something like that when you program it? And that's the reason why is because all the bits are, it's serial. It's a big shift register. And it runs at like a megahertz, so it's pretty slow. Okay, and that's basically it. Any questions about that? So exam 1 will just cover that stuff. We have, so take the exam anytime this week. Next week we have spring break. This week, just demo lab, lab 2 to Philip or I. What we're looking for with the demo is we're just going to want to see your code, maybe briefly describe how you did it. I mentioned in the lab sheet that there are multiple ways to do it. Specifically, there's the performance counter, and then there was the USleep, the sleep function. So the difference there is that the performance counter is a kind of a clock that runs independent of the CPU, which you can read, and you can measure time, the amount of time that's elapsed. So if you use the performance counter, the idea was that your code would keep checking it until it reaches a certain value. It's kind of like waiting on the clock. You know, you look at the clock and you say, okay, I'm going to sit here and wait till 10:30, and you just sit there and watch it until it hits 10:30, and then at which point you know that, well, it's time to take the LEDs and turn them off. For instance, if I'm now if I finish with the duty cycle. That's the general idea of using the performance counter. The other approach is to use the sleep function, and the way that works is it's a busy loop, and it's written so it basically just loops, and the number of times it loops is based on the CPI, the number of cycles per instruction, and the number of instructions in that loop. So they programmed that, they calibrated that to go into a busy loop for a calibrated number of iterations to match the amount of microseconds you want to sleep. So it doesn't use any kind of external timer or external clock at all. It's just a loop. The problem with using the sleep function is that when you go to a sleep, like you say, it basically assumes that the instructions don't require any time to execute, right? So you say, I've got the duty cycle, I want to set the duty cycle to a certain amount of microseconds, and I'll wait for that amount of time after I set the LEDs high. But it doesn't take into account the amount of time it took to call U-Sleep, for instance, right? And while you were calling U-Sleep, that was extra time you were leaving the LEDs on. Now, what is the actual impact of that? Very small. I mean, it's negligible. So we're fine. You're not going to lose any points if you do it that way. But that was the reason why we gave you, there's those two options. So we'll ask you, how you did it and look at your code, and then we're going to ask you to be able to change both of the parameters, the PWM frequency and the dim period. So if the dim period, if we say set it to a quarter second, it should go real fast, or we'll say set it to 5 seconds, it should go very slow. And then I keep saying piecewise linear. The pulse width modulation, the objective there is we want to know how slow you can make that before the lights start noticeably flickering. At some point, if the PWM is slow enough, they'll flicker. You'll be able to perceive flickering. How slow? When do they start flickering? Because if you make it fast enough, it just looks like dimming, and they look like they're just on, but at a certain brightness level, right? So now you have to be careful, because if you use, depending on how you wrote your code, you may have constraints on those two parameters. For example, your code may force you to have a dim period that is at least 200 times that of the PWM period, right? Depending on how you wrote the code. If you may have restrictions in your code of how you can set those parameters. So we'll ask you, the idea is just to make sure you understand what the implications of that are. You guys with me? So that's what we'll do next week, and then after spring break, I'll introduce the next lab, which, as you probably guessed, it'll be on System Verilog. We're going to be combining some hardware with the software. And you might say, well, how common is that? Very these days. Apple comes out with a new chip. It's a little tiny piece of it is ARM processors running code that mostly just doesn't do anything, but it's kind of the master of the system, but it doesn't do any performance critical heavy lifting. All of the computational photography, video encoding, tracking, all the features that you use on your phone, multimedia features, those are all handled by custom hardware components that are put onto that bus, on the system on chip bus, which are slaves, but they do the heavy lifting. You send them a workload to process all the pixels coming from the camera, and they do it very fast, and usually with very, like 8-bit operations. Whereas the ARM processors on your phone just run Linux and Android or iOS. So every time there's new capabilities, like some really cool new resolution or new feature, Face ID or something like that, that's all from designing hardware and putting it into that chip. So that's what we're going to do in the next lab. Except, we're going to not do anything super complicated, just enough to have the hardware and software communicate with each other. Okay, all right, well, that sounds good. We can stop a little early. If you have any other questions, let us know.